let's summarize the lecture for tangent plane linear approximation and toggle differentials. Let's start with the function itself. Let's say either z equal to f of x and y, an explicit function, or a capital F of x and y, and z equal to c, an implicit surface. So one thing that I want to make sure is that when we're talking about surfaces, when we're talking about explicit functions, again, the graph of the function is a surface, and we can write it in the format of the implicit surface. So let's write this function in format of an implicit surface. F of x and y minus z equal to 0. When I'm writing it this way, then I can basically assume this is f of x and y and z equal to 0, so it looks like then implicit surface. What is the difference between implicit surface and explicit function? Explicit function, I can solve for one of the variables. Implicit function is an equation including all the variables, so I can assume locally if I plug in points, it would become, for two of the variables, a third variable is going to be a function of those two variables locally again. Now, what we learned is that the gradient of f, the explicit surface f, capital F, at a point A and B and C is orthogonal to tangent plane at A and B and C. We can use this, then that means that this gradient of f, because it's orthogonal to the surface, is then normal to the tangent plane, if it exists, by the way. This has to continue if it exists. That means if the tangent plane exists. So what do? I try to use this to find the equation of the tangent plane. And so I dot this with x minus a, y minus b, and z minus c, which is, by the way, where are a and b and c coming from? A and b and c are the points on the surface of the function, basically, or implicit surface of the function, equal to 0. And you can plug in a and b and find c, basically. Now, doing that, I will get f sub x at a and b and c times x minus a plus f sub y, capital F, at a and b and c times y minus b plus f sub z at a and b and c times z minus c equal to 0. Notice that there are basically over here, when I'm plugging in, I have to plug in the point in the partials every time to find this equation of the plane. Now that I found the equation of the plane, let's put in big box. The next thing is that how do I linearly approximate? Linearly approximate means using the z in this plane to find the z values that are near point A and B and C. So z here is the z equal to f of x and y, or the z in the implicit function, that is for points near A and B. This is linear approximation. So in this case, let's just assume they drop the implicit surface, rewrite this in the format that we had before. So the format that we had before, now, if I want to use z equal to f of x and y, what I'm going to get is f sub x, according to that, is going to be just f sub x of x and y. F sub y is just going to be f sub y of x and y. And f sub z is just going to be -1. So plug that back in to rewrite the equation, and I get f sub x at a and b instead of a and b and c times x minus a plus f sub y at a and b times y minus b plus minus z minus c equal to 0 because it's an equation. Let's write it equal to 0. Now, going from this and solving for z, I'm going to get z is equal to, this is basically minus z plus c, right? Z is equal to c plus f sub x at a and b times x minus c, a plus f sub y at a and b times y minus b. Now I want to add one extra details in here. What was c? C, if I have the explicit equation, c is just f of a and b. So here now I got the linearization. Let's write it down. L at a and b of x and y is equal to f of a and b plus f sub x of a and b times x minus a plus f sub y of a and b times y minus b. And that's the linearization. So you can see that there are basically one implies the other, and it goes back and forth. Now, one thing that I haven't said talked about is the total differentials. Let's go back to the total differentials. If basically over here, if I want to compute the total differentials over here in the explicit format, total differential x minus a is going to be delta x, y minus b is going to be delta y, and z minus c is going to be our total differential. So I'm going to write it as dz, so this is going to be dz. I'll take it to the other side, and I get f sub x at a and b times delta x plus f sub y at a and b times delta y. And that concludes the lesson.